There's been a lot of debate about whether large language models are memorizing or generalizing. And recently with a paper from Apple saying that large language models are actually memorizing, together with the ARC AGI challenge also showing that they are memorizing. I think it's important to also highlight that they are capable of generalizing, and that there's one very important concept called grokking, through which they do generalize. So this video I will explain what grokking exactly is, because it's a term that's been thrown around a lot and it's a buzzword, but the concepts are actually very familiar to what we've had in the past. It's just old school machine learning. So let's look at our little artificial intelligence, and it's learning on data right now. It just has a straight line through it because it has not ingested it yet. Well, let's train it. Look at that. That's better, but it's overfitting. It's way too complicated. The curve will not generalize well. We want him to learn something that will transfer to the real world. If we train the model too much on this data, we will just start to memorize it even more, right? Well, look at that. A perfect line. How is this possible? After a lot of training, he goes from memorization to generalization. Seems like magic. Well, this is what grokking is. So let's say we start to train our model, and we want to train it to enjoy hiking. But he really has to enjoy it, so we want to see a smile on his face. He really has to enjoy it. And not just memorize the words and say that he likes it, but actually understand it. This graph is a loss function. We see the error rate on the y-axis and the weight factor on the x-axis. The goal for our little AI is to find the point where the error rate is the lowest. We do that through gradient descent. You should take note of the local minima and the global minima. We are trying to get to the global minima. There the error rate is the lowest, and the local minima are just gonna be annoying for gradient descent, because gradient descent is based solely on the point where it's standing. It can only see the curvature of the graph at the point where it's standing. So, in order to find the lowest point, you will see if the curvature is flat, because a minima is always flat. That's why local minima are dangerous, because he can get stuck in these ditches. And look at that, he's stuck. Well, not until we up the learning rate. The learning rate is basically the step size of the AI, so upping it makes it easier for him to step outside of the ditch. Now, after a bit more training, we get him out of the ditch and the performance gets better. Or, in the case of grokking, it gets more generalized. And this is basically what happens with grokking. Our model was stuck in a local minima and got out and got to the global minima. So as we saw, learning rate is something that influences grokking. Another annoying thing, except for local minima, are saddle points. Saddle points give the same problem for the robot. They are flat and he doesn't know how to get out of them very easily. So it's possible that overfitting happens in the local minima, and memorization is just a thing of the past if we train enough so we can get to the global minima of understanding. Well, when we use regularization, we can actually get rid of this local minima, because regularization punishes complexity, and we saw that our function was very complex. So it worked. The graph is now compensated for regularization. We don't need that high of a learning rate now. Even with a small step, our robot easily gets to the global minima thanks to regularization.